Today, and the stuff that we talk about today isn't on the exam. I mean, for the interest of the class, we really should move on to chapter 4, but there's really important things that we didn't talk about because we were dealing with your worries about nomenclature. And in some ways, what I'll tell you today is way more important than all of that nomenclature stuff because it's how the molecules we're going to talk about actually influence your everyday life. Like you have experience tasting, touching, and smelling some of these molecules, and I want you to know about them because I think I may be the last person in your life who will tell you about them, and this is stuff I want you to know. We're also going to talk about, how interactions between molecules lead to a lot of the phenomena we can observe in daily life, like how does soap work, and what are bubbles, and how do cell membranes work, and why is vegetable oil a liquid but animal fat's a solid. These are things that you basically cook with and work with on an almost daily basis, and I want you to know some of the chemistry that's going on, just because I feel like that's part of education. So I want to just talk briefly about molecules that you can taste and smell. So you've learned about carboxylic acids, and they have characteristic tastes and smells. So, for example, if the carboxylic acid, I can't spell carboxylic while I'm talking anyway. Carboxylic acid, the simplest one that we've dealt with so far is acetic acid, or the proper name is ethanoic acid, but this is in vinegar. And you know how vinegar tastes. It's just sort of tart, so you'll use it sour. You'll use it in salad dressings or other times when you need a little bit of acidity. Another sort of famous carboxylic acid that's often in food is citric acid. This has got 3, and no, I don't want you to memorize that this molecule is called citric acid. You don't need to worry about that yet. You'll learn that in 352 in more detail. But this molecule, citric acid, is found in, yes, citrus fruit and other things as well, and it's quite tart. So if you've eaten those sour candies, Sour Patch Kids or whatever, got a lot of citric acid in them, and that's what makes your mouth go in the sort of puckered up face. Now, it's not all pleasant with carboxylic acids. As they get a little bit longer, they have an interesting characteristic smell. So behold, butanoic acid or butyric acid. This is the one that smells like vomit. And some of these longer chain carboxylic acids smell like sweaty feet. So, I have teenage boys, and their sock hygiene is terrible despite our efforts to the contrary. Limburger cheese, also like stinky cheese, depending on the kind of cheese that you're dealing with, will have some of these molecules in it. So if you want to know why vomit and feet smell gross, behold the molecules that smell that way. Another carboxylic acid that you'll encounter, or that we'll talk about a little bit later, if it's called a fatty acid, and it's if you have a carboxylic acid attached to a chain that's so long that the molecule is no longer volatile. So we'll do 2, 4, 6, 8, 10, 12, 14, 16. That's a 16 carbon fatty acid. This one's called a saturated fatty acid because it has no double bonds in it, no pi bonds, rather. Okay? And fatty acids you can get from fats or oils. Your body actually makes fatty acids from fats or oils, and then it can degrade the fatty acids to turn them into acetyl-CoA and get energy from them. We'll talk about that when you take 352. But another interesting use of fatty acids is they can be used as soaps. So we'll talk about that in a little bit. Not necessarily the fatty acid, but its conjugate base. Okay, so carboxylic acids, smelly at longer, intermediate length, soaps at really long lengths, and sort of tart otherwise tastes. Now, you're wondering, do I need to memorize all those structures? You know, probably not. I'm not going to ask you which of the following is citric acid. That's sort of a boring exam question. But I could ask you which of the following tastes tart. And even without having tasted them, if you recognize the functional groups, you can be like, oh, it's probably the carboxylic acid. Does that make sense? Yeah?
So will it still have the names of it though? Like, let's say, which the following tastes tart?
I'll show structures probably.
So without the names?
Without the names, yeah.
So we will have to know.
You'll have to recognize a carboxylic acid, which I think you should do already because of the nomenclature stuff, yeah. Okay, so let's do esters. These are kind of fun because unlike the carboxylic acids, they do not smell like vomit. In fact, at low molecular weight, low sort of small molecule esters smell either floral or fruity. So some of you may have actually done this experiment in high school chemistry. You can make, an ester has a R group on one side and then another R group attached to the oxygen. You can actually make esters chemically from two precursors. You need carboxylic acid and you need an alcohol. And the condensation reaction that puts these two together is you'll learn about in 352, but you end up losing water to make the ester. The R prime group comes from the alcohol. So you can make these pretty simply. Sometimes in high school chemistry classes you will have done this and you'll choose the carboxylic acid and the alcohol such that the ester has a characteristic smell. Let me just show you a few of them that are kind of fun. So if the ester looks like this, and I'll just highlight, this is the carboxylic acid portion, this is the alcohol portion. If the carboxylic acid portion looks like this and the alcohol portion looks like this, that is the smell of cherries. So whether you're actually dealing with cherries or just making a molecule, you smell that, it smells like cherries. Your brain will recognize that as cherries. And sometimes these are used as flavor additives in foods. So if we change the structure a little bit, oops, went to the eraser. Then you have apples. Isn't that interesting that your nose can sense the difference in structure between the cherry ester and the apple ester? And this is an important principle in organic chemistry. Shape and structure are related to function and properties. So you're going to see a ton in OChem how subtle changes in structure change properties and function. And if we can learn those rules, we now have power to make molecules that do interesting and useful things. And that's a really key principle in organic chemistry. Let's see, I wrote down one, but I don't know what it tastes like. So let's just do one last one. If you want to look it up, there's actually a huge graphic that's available. Just Google fruity ester smells and there'll be this big table that has on the one side carboxylic acids and on the other side alcohols, and you mix and match them to get different fruit smells, different plant smells. It's kind of fun. So anyway, this is the one that, and there are a few that smell like banana. So I might ask a question, which of the following smells like strawberry? And you're like, was I supposed to memorize that structure? No, just pick the ester and you'll be close enough. It's not like I'm going to have 7 esters and you'll need to know, well, that one smells like almonds, but that one smells like strawberries, but that one smells like bananas. That's beyond the level of what we want to do. If you want to learn all that, knock yourself out. But just in general, esters smell kind of fruity. Now, the other place in sort of foods that you encounter esters are in fats and oils. So a fancy word for a fat or an oil is a triglyceride, which is a word for basically a triester. So in the triglyceride, you have an alcohol portion, which I'll highlight in orange, that has 3 oxygens. So the precursor to a triglyceride, this portion that I'm showing you in orange, is either called glycerol or glycerin. And then each of those oxygens in the triglyceride is attached to a long chain fatty acid. So let's just do 2, 4, 6, 8, 10, 12, 14, 16. 16 chain carboxylic acid attached to the alcohol oxygen via an ester. That's sort of bothering me that those lines aren't meeting. Okay. And then I'm going to do something that you guys will hate, but, you know, yay me, and copy and pasting because I don't want to redraw everything. You can put, if you're in a hurry and you don't want to draw the rest of the chains, just do this attached to the alcohols. So this is here is the glycerol portion of a triglyceride. This is the fatty acid portion of a triglyceride. So if I ask you which of the following is a fat or an oil, again, you don't need to memorize that particular structure, but a 3-carbon thing with 3 oxygens and each is involved in an ester with a long chain fatty acid, that's a triglyceride. This, what I've drawn here, is an example of a saturated fat because there are no pi bonds. Because you'll find that molecules that you can smell are generally low molecular weight. They need to be volatile enough to sort of evaporate and get in the air. Molecules that are longer in molecular weight don't tend to have the same smell. So nobody opens up oil and smells it, vegetable oil, and smells it and says, it smells fruity. I mean, it does have a smell, but it's different. Let's see. Let's give you an example of an unsaturated fat, because those are food labels. Unsaturation has to do with the presence of pi bonds in one of the fatty acids. So here is, we're going to draw a fatty acid that has a pi bond between 1, 2, 3, 4, 5, 6, 7, 8, 9, carbon 9 and 10. So 2, 4, 6, 8, 9, and 10. All right. And the double bonds in natural fats and oils are all cis in configuration. This double bond is called unsaturated because unlike carbons 9 and 10 in the saturated fatty acids that have as many hydrogens as it is possible for them to have, the unsaturated fatty acid portions are missing 2 hydrogens. Do you see how 2 carbons bonded to each other should have 4 hydrogens on them in a fatty acid? Do you see how this one only has 2? That's why we say pi bonds are unsaturation, okay? All right, and we will see soon that the presence of that double bond influences the properties of the triglyceride. For example, just as a preview, a saturated fat is generally a solid. So fats that are rich in let's see. And in general, the term fat is like triglycerides from animal sources. Oils are generally triglycerides from plant sources. But in general, fats or oils that are totally saturated are solid, whereas fats or oils that have unsaturation in them are generally liquids. And we'll talk about why. You'll see on food labels mono unsaturated. That means 1 double bond. You'll see polyunsaturated, that means multiple double bonds. And then the other thing is you'll see omega-3 unsaturated, and I gotta check my notes for one of those to draw something that's realistic for you. And I got nothing today, so we'll have to do that soon, but not now. I don't know. Do you want to know about omega-3s?
Yes.
You don't really care? Yeah? All right. So for I'm worried I'm going to get it wrong, but that's okay. You guys are forgiving, right? Sort of. Okay, so you've heard of omega-3 fatty acids. And so why is this a thing? Well, okay, some triglycerides, and I'm just going to copy this, have fatty acids that have multiple double bonds in them. And as I said, the natural double bonds are all cis. So this molecule has a cis or Z double bond between carbons 9 and 10. And I'm just going to draw in some additional saturated or unlevel degrees of additional double bonds. So this would be an additional pi bond between carbons 12 and 13. Interestingly, these double bonds are generally not conjugated, that is, they're not adjacent to each other. And then let's see, we'll have, I think if I'm remembering the structure right, there's a pi bond between 15 and 16, and then this is 17 and 18. So this is an 18 carbon fatty acid attached to a triglyceride, and it has 3 double bonds, so it's a triunsaturated fat or a polyunsaturated fat. They are 9Z, 12Z, and 15Z. Now, where does the omega and the 3 come from? It turns out that that we have lots of different ways of talking about molecules and which carbon we're interested in. You can, of course, number the carbons, but sometimes if you're dealing with chains that have different numbers of carbons, that can be challenging. So sometimes we pick a carbon that we are interested in, say the carbon that's involved in the ester bond. So we'll just call that our point of interest. And sometimes we will start counting relative to that point of interest. And when we do, we use Greek letters to indicate distance away from the point of interest. So the alpha carbon is the one that's adjacent to, A for adjacent, alpha adjacent to the point of interest. And then we just start going down the Greek alphabet from there, alpha, beta, gamma, delta, until we forget what the Greek letters are. And that's about the point at which most people forget. I happen to know that the next one is epsilon. So yay me, I'm not sure what's after epsilon. But so for a really, really long chain, we give up, and then we just go to the end, and the last letter of the Greek alphabet is omega. You know that because one of the titles of Christ is Alpha and Omega, the beginning and the end. So the omega is the end of the chain. And then this is the first atom at the end of the chain. This is the second. This is the third. And omega-3 fatty acid has a double bond starting at the third carbon from the end. That's where that term comes from. Okay? Now, what's the big deal with omega-3 fatty acids? They are associated with lower cholesterol and better cardiovascular outcomes. You can find them, and that's true, I think, generally for unsaturated fats. The biochemistry and the pharmacology are beyond the scope of the course. You'll have to learn about that later in terms of why unsaturated fatty acids tend to lower cholesterol and prevent negative cardiovascular outcomes. At this point, the studies have indicated that that's probably the case, and therefore it's now a point of marketing. Anything that has a health benefit is going to be marketed to you. And so there are various food products that people are anxious to tell you now contains omega-3 fatty acids. For example, you can get eggs that are enriched in omega-3 fatty acids. How do they do that? They feed omega-3 containing fats to the chickens, and then when the chickens lay the eggs are enriched into fatty acids. Questions about that? Okay. Let's see. So we needed to move on past esters. I got talking. Oh, all right. Let's talk about stenches. Various stenches. Amines. Amines are great. They are interesting because, as you've seen, they can be bases. But at small molecular weight, they have unpleasant smells. So behold the simplest amine, which is ammonia. And that's a household chemical that you can smell. And I don't know, how would you describe the smell of ammonia? It's just unpleasant. It's sort of acrid. Nobody's like, the smell of ammonia, right? It just kind of, I don't know how I would describe that smell, but you've probably smelled it before, and it's kind of, it's not like, oh, I'm going to throw up. It's like, oh, my nose hurts. Now, if the amines have a little bit more carbons, the smell starts to get unpleasant even more. So this is called trimethylamine, and it smells like fish. And some of and that's not just trimethylamine, some of the other amines of similar shape smell like fish. So the fishy smell, probably amines. Now here's an interesting story. If you go to a pub in Britain and you order fish and chips, probably they also give you what fruit with your fish? Lemon. Okay. Lemon contains citric acid. So now let's try to reason why on earth they're giving you lemon with your fish, except, the taste of lemon is kind of nice in mild doses. So what do you suppose happens to the fish smell when you have this carboxylic acid present? Well, pKa of the carboxylic acid is what? 4? So you could imagine that the amine acting as a base removes the proton from the carboxylic acid, and you get now the corresponding conjugate base, the ammonium ion, which has a pKa of 11, and then you get the conjugate base of the carboxylic acid, which I'm just going to abbreviate like this. Turns out that, as I said, things that you can smell are generally volatile. That means they can get in the air and therefore into your nose. The ammonium is no longer volatile because it is charged, and it's going to be held in solution by the attraction between it and the counter ion. So you put lemon on the fish, it no longer smells as fishy. So in addition to the taste, it's to make you have a more pleasant experience because you're voluntarily eating fish, but fish sort of smell like fish. So this lemon helps fish smell less like fish. You want to try a fun experiment, go to the seafood section of your favorite grocery store and pick some fish that still has eyes in it, and put it in your trunk. There's only a few hot days left in the year, so please do this weekend if you're going to. Put it in your trunk, wrap it in foil, and then squeeze lemon all over it. And then you need you need a friend. I was getting nauseous. No, I'm just kidding. You need a friend to do the control experiment without the lemon and see whose trunk smells worse after a week. All right? So between now and conference, that's your assignment, the rotting fish experiment. Now, it gets worse because some amines not only smell like fish, but they smell like death. So, and these amines have interesting names. 1, 2, 3, 4, 5. They're actually breakdown products from amino acids that are in your proteins. 1, 2, 3, 4, and then 1, 2, 3, 4, 5. And the names should say it all. This is called putrescine for putrid, and this one is called cadaverine, which smells like death, rotting flesh. So if I say which of these smells like, which of these molecules would a zombie smell like? then you know the ones to pick, probably the amine. Or which of these smell like fish? Probably the amine. Okay, questions about that? Some amines taste bitter. There are a class of molecules called alkaloids that are often poisonous, that have a bitter taste, and people theorize that the reason they taste unpleasant to us is because they're not good for us. And I can't really think of examples of using amines in cooking because of the whole death thing, other than the fish. So there you go. All right, while we're talking about stink, I feel like we're in the Mr. Grinch song. This is the stink. Amines are the stank. And then thiols are the stunk, really bad, okay? Stink, stank, stunk, da 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 da. All right, so thiols have a characteristic smell. They basically smell like skunk or rotten eggs. And there's a whole diverse smell palette of thiols that you can get into if you want to. Some of them are actually pleasant enough that they're used in cooking. As an example, here are a couple of thiols, some of which are actually used as odorants in natural gas. So it turns out that propane and butane and methane are odorless gases. We use them for furnaces and water heaters and cooking, but the problem is they don't smell like anything, so you can't detect a leak, and if you can't detect a leak, you can't turn off the gas before you light something, and then the whole place goes up in smoke, right? So ever since the very beginning of using natural gas, we have added small amounts of smelly chemicals to the natural gas so that your nose can smell it and say, that doesn't belong there, and then detect it. And so what you smell when you smell natural gas is not actually the methane, because methane doesn't smell like anything, it's instead the thiol that they're putting in the natural gas so that your nose can detect it. So natural gas odorants are often thiols. When you smell skunk, this is what you're smelling. Here are a couple of actual molecules from the skunk stink sac. And they are all low molecular weight thiols that are relatively volatile. So if I say, which of the following smells like skunk, just look for the thiol, right? Now, sometimes there are some pleasant thiols, or thiols that are sufficiently pleasant that we use them in cooking. Garlic and onion in particular are often used in cooking. You're supposed to saute the garlic until it starts to smell more powerful. You're actually releasing the molecules, the smell molecules from the garlic. Same thing with the onion. Here is one from onion. It's a weird sort of two thiols on the same molecule, and that's found in onion. And then there's a related, it's not a thiol, but it is a sulfur-containing molecule, and I think it can break down to release thiols. But this molecule is present in garlic, and it's specifically, I think it's released when you actually chop or crush the garlic. So the characteristic smell of garlic is that. Some people like it in cooking, some people don't like it on dates, so use with caution. All right, let's talk about alcohols. We won't say too much about these. Simple alcohols don't necessarily taste like anything. This is ethanol. This is isopropanol. This is rubbing alcohol, so you don't want to drink this, and you shouldn't drink that. Let's see what else. Polyols, that means molecules that have multiple OH groups, are often sweet. So, for example, here are a couple of polyols that you will get really familiar with in 352, and maybe in a little bit in 351. The molecule I'm drawing is a 6-membered ring that's decorated with alcohols. and the ring also has an oxygen in it. This is called glucose, and your body uses glucose, and that's the starting point for metabolism and glycolysis and so on. But if you've ever tasted glucose, you might be like, what's wrong with me? It doesn't actually taste that good, and that's because what tastes really sweet to you is this thing called sucrose, or table sugar. And I'm drawing it fast, and I don't want you to memorize the structure of it yet. I'm 352, you'll definitely need to know the structure of glucose, and we'll give you the tools to do that. But for right now, you can just see this is sucrose, or table sugar, all kinds of alcohols, and it tastes very, very, very sweet. And if you have a sweet tooth, that's what your brain is craving. Now, even a simple polyol tastes sweet. This is called ethylene glycol. And this is not something you should eat. This is antifreeze. So on the label of antifreeze, it says keep away from pets and small children, because it tastes sweet and they're not going to know the difference. And it can actually do quite a bit of damage if you ingest it. I don't exactly know why. And then briefly, there's interest in making molecules that taste sweet but don't have, we haven't yet talked about why sugar can be dangerous. That's a story that stays till 352. The short answer is sugars are secretly aldehydes and ketones, and those are very reactive molecules that can do a lot of damage. But not that that stops me from pursuing sugars vigorously. But some people have tried to develop sugars, molecules that will taste sweet, but are not metabolized in the same way or at all. And this is an artificial sweetener called sorbitol. And you can see it's a polyol, and that's why it tastes sweet. Okay, I think on your problem set we have a few more tastes to do. One of them is salt. That's boring. What tastes like salt? Salt. All right, yes. Ions taste like salt. So NaCl, sodium plus, Cl minus. That's, in general, electrolytes. That is, things that have that are ionic compounds that dissociate in water. Will generally taste salty. How about the fourth or the fifth flavor that a lot of us didn't know existed? We were taught salty and sour and sweet and spicy, but umami is a legitimate fifth flavor, and this is basically the taste of a particular amino acid. There's a few other molecules that also taste like umami, but this is the major one. This is an amino acid, and I'm drawing it in the form, I'm doing the hard work for you, I'm drawing it in the form that it would exist in at physiological pH. If it has a counter ion, overall it's neutral, and this is the famous monosodium glutamate that is often added as an additive to, for sort of a savory umami taste. Okay, so that's it. But this amino acid is found all the time in proteins. There's some indication that one of the reasons salt tastes good to us is because protein sources generally are a little bit salty, and so that may be one of the reasons why we're sort of attracted to the salty taste. All right. So if I say, which of the following tastes like umami, you're basically looking for that molecule, but look for the amino acid in the form that it would exist in at pH 7. Okay, lastly, I want to do spicy, and spicy is just not a particular functional group. Spicy is a particular shape of molecule, and it binds particular receptors that your body interprets as being heat, even though there's actually no caloric heat associated with it. So these molecules trick your body into thinking, ouch. And there's a huge interesting story here, but we don't really have time for it, and you can learn more about it later if you want to. So the most famousest, oops, what happened there? The most famousest of spicy molecules is capsaicin. You've likely heard of that. So capsaicin is a bunch of really interesting functional groups all at once. So here's an ether, an oxygen that's bonded to 2 carbons. Here's what's called a benzene ring. There's an alcohol. Then let's see, there's a nitrogen and a carbonyl carbon. That's an amide functional group. And then there's a double bond there and 2 carbons, and that is capsaicin. And yeah, that binds to a receptor. The receptor it binds to is actually something related to vanillin, It's called a vanillin binding protein, I think. Maybe I'm getting this totally wrong. There's a short aldehyde called that's present in vanilla. Capsaicin is structurally similar to it. Don't write that down. I don't necessarily care that you know it. But basically, this portion of the molecule binds a receptor, and that triggers the ouch response. There are some other sort of pungent molecules as well. It's difficult to see a lot of structural similarity. Sometimes different molecules that have vastly different structures still can fit into the same receptor. So there's not necessarily a structure-function story that I want you to take from this, other than I want you to have seen the molecules that cause pain when you eat spicy things. This one is totally different, but it's found in mustard and horseradish and wasabi. Let's see. Oh, and then there's, I read something recently, I thought this was just kind of cool. There's some thought as to why things like peppers, jalapenos and so on, make capsaicin, why they're so spicy. And the idea is that the seeds inside are relatively fragile, and so if animals that have molars and teeth eat the peppers, they often chew up the seeds, and then the seeds aren't viable anymore. But if birds that don't have teeth eat the peppers, no problem. The seeds go through the bird intact and are accompanied by a little packet of fertilizer when the bird drops its stuff, and then the seed grows. And so evolutionarily, the plant is like, I mean, this is not what's actually happening. The plant's like, yes, if birds eat peppers, that's good. If cows eat peppers, that's bad, right? And so the pepper makes a molecule that makes the cow go, ouch, but not the bird. And anyway, so that may be one of the reasons why peppers are spicy. Okay, so that is our survey of tastes and smells. I've tried to reassure you about the kinds of questions you're going to experience on this issue. Any remaining anxieties about that we want to talk about? Yeah?
Is it like you need to know like acids from like combinations, or what's like?
So it's basically any of the short molecular weight butanoic acids will smell that way. I'm sorry, any of the small molecular weight carboxylic acids will smell that way. You've got some flexibility on number of carbons, 4, 5, 6, they all kind of have that smell.
So carboxylic acids that are short smell like vomit.
Yep, except for the really short one. So you got this really short, which is vinegar, which is not unpleasant in small doses, and then you've got the intermediate, which are really unpleasant, and then you've got the long ones that you can't smell anymore.
And then I thought I put carboxylic acid smells tart.
They taste tart, so sour. This is why they taste tart or sour. They taste tart, but the slightly longer ones smell bad. So when Paul Hollywood on the Great British Baking Show talks about the fruit really adds that acidity, what he's talking about is the fruit added the carboxylic acid to the thing, and you can taste it as sourness. Okay, others? All right, so now I want to talk about non-covalent interactions. These are intermolecular forces. I don't think I really need to introduce them to you because you've encountered them in general chemistry. Most of you could rattle them off. There are ion pairs, electrostatic interactions. So this would be the attraction between a positively charged ion and a negatively charged ion. And this is basically Coulomb's law. Now, in 105, 106, you maybe called this an ionic bond, and you maybe thought it was super strong. And the reason you thought that is because somebody told you, yeah, if you put salt on a hot plate, you have to heat it up to like 3,000 degrees before the sodium and the chlorine ions move away from each other, right? But remember, in 351, strength is always relative to something. So if the attraction between sodium and chloride is so strong, then how come salt dissolves in water? And you probably already know the answer to that, but to know the answer, you have to think about, if you're going to break apart one interaction, you have to think about what you're replacing it with. So we need to talk also about ion-dipole interactions. Before we do that, I just want to point out that in organic chemistry, we're interested in things that are more complicated than sodium and chloride. So this is a quaternary ammonium ion. It's positively charged. This is a negatively charged carboxylic acid. They will be attracted to each other because of opposite charges attract. I'm not going to write out Coulomb's law, but you know the larger the charge is, the stronger the interaction. You also know that the closer they are together, the stronger the interaction. Now the question is then, how do you ever get two ions apart? Because you know that can happen. You add salt to water and suddenly the salt crystals are gone. And floating around in solution, the sodium and chloride ions are just around each other, but they're not sticking really close together. And this is because of what are called ion-dipole interactions, which arise because of electronegativity differences in molecules. So if we look at water, you know, of course, that oxygen's more electronegative than hydrogen. So you're accustomed, yes, to the fact that the oxygens have a partial negative charge and the hydrogens have a partial positive charge. You good on that? We sometimes draw this with a dipole. Dipoles are vectors. You add up the individual bond dipoles and you see that this side of the molecule has a partial positive charge, this side of the molecule has a partial negative charge. And what happens when a salt dissolves is that the sodium ion is surrounded by oxygens from water, oriented so that the delta minus end of the oxygen is pointing towards the sodium. So in dissolved salt, we have replaced an interaction with Cl minus, and that's an ion pair interaction with many ion-dipole interactions. Now you learned that ion-dipole interactions are weaker than ion-ion interactions, and that's true, but many weaker interactions can fully compensate for one stronger interaction. Does that make sense? So in general, this is a preview, but processes that happen in chemistry are called spontaneous, meaning they are downhill in energy, which another way of saying that is free energy delta G is less than 0. That is true when the interactions that you form in a process are stronger overall than interactions that you lost, okay? So salt dissolving is, there used to be an ion pair and that's pretty strong, but we put it in water and now we replace those ion pair interactions with many more ion dipole interactions. I'm gonna leave it to you to imagine what Cl minus, well, we'll just draw a couple of hydrogens in water oriented towards Cl minus, etc. we would call that a solvent-separated ion pair or a solvent-separated ions, okay? Questions about that? Do you see how we're reasoning our way through that? That's pretty simple. I've asked you about that on the problem set because I want you to be able to think about these things critically and challenge some of perhaps your long-held beliefs that are true, but only from a certain point of view. Is an ionic bond strong? Relative to what? Why does it take so much heat to melt sodium chloride? Because you're not replacing the interactions with anything there. You're just trying to brute force provide enough kinetic energy that the ions move away from each other. But at room temperature, if you got water present, no problem, right? You don't even have to heat water up to dissolve sodium chloride. Does that make sense? I mean, it is 8 a.m., but come on. Yes? Yes. Sort of? All right. All right. There are also dipole-dipole interactions, and the most famousest of these is the so-called hydrogen bond. The hydrogen bond is especially strong kind of dipole-dipole interaction because hydrogen is so small and the atoms involved can get close to each other. And in general, for all the non-covalent interactions, proximity, meaning closeness, increases the strength of the interaction. So with ion pairs, with ion dipoles, with dipole-dipole interactions, the closer you get together, the stronger the interaction is. So you've seen, the classic description of a hydrogen bond in water, the delta plus on one hydrogen to the delta minus on an oxygen. And in water, in a glass of water, those hydrogen bonds are strong, but they are also transient, meaning they are rapidly changing. Meaning at one moment, water molecule A, oops, I'm erasing him, is hydrogen bound. I'm doing it again. I wanted the laser pointer. The water is hydrogen bound to this water molecule, and then in another second it will be hydrogen bound to another molecule. And it actually gets more complicated than that, though we'll maybe leave that for another time. The surface tension of water that you have experience with is because of the strong hydrogen bonds with water. This is why water beads up on a surface, especially on a Teflon surface, because the water molecules are just holding on to each other via hydrogen bonds. Do I need to say more about hydrogen bonds in water, or do you basically got that? Okay, now we're going to talk about the hydrophobic effect, and the hydrogen bonds are going to play a role in that later. That's the explanation for why water and oil don't mix. Okay, I anticipate I will need Monday to get through non-covalent interactions, and then on Wednesday we will move ahead to chapter 4, and I will adjust deadlines as needed. Good luck to the 75% of you that haven't taken the test today, and I will see you on Monday.